What if science isn't limitless? Not due to lack of time or resources, but because it's inherently unable to answer everything. Sounds unsettling? Even more so knowing that scientists have recognized this for ages, and some have even proven it. Hello, dear guests and viewers. I'm John, and today we'll continue our journey into what science truly is, at its most fundamental level, exploring its core ontological questions. Why? To understand where the scientific method ends, and what lies beyond it. To avoid being misled by technological progress that seems unstoppable, yet whose limits are defined not by machines, but by reason. This will help us approach, with greater clarity, the question of whether a rational principle governs the universe. As usual, I'll ask my assistant and colleague in this inquiry to clarify the key concepts.
The human brain's capacity. Systemic gaps between scientific disciplines that no longer communicate effectively. These can't be fixed with better tools. They're built into the very nature of knowledge itself. Logical limits arising from the structure of formal systems. Cognitive constraints of the human brain's capacity. Systemic gaps between scientific disciplines that no longer communicate effectively. These can't be fixed with better tools. They're built into the very nature of knowledge itself.
And that's the heart of our concern. We keep building ever taller towers of knowledge, but their foundations remain logically limited, cognitively overloaded, and poorly connected. Since the early 20th century, the number of scientific disciplines has exploded from around 50 to over 10,000. Science has become an archipelago, each scholar stranded on their own island. Climate scientists, physicists, economists, sociologists, they each speak a different language. We think we're having a unified conversation, but in truth, we're talking past each other. Can we restore dialogue among these fragmented fields? That's the challenge of scientific fragmentation, a century of rapid growth. We often picture science as a sphere, but every sphere has a center. The farther knowledge spreads, the weaker the connections. We start with a holistic vision and end in fragments. Science's information entropy grows, like an expanding universe, more knowledge, fewer links. When physics can't understand biology, biology can't grasp philosophy, and philosophy becomes irrelevant, we end up with a Babylonian tower of knowledge. It's like the fable of the swan, the crayfish, and the pike, each pulls their own way and nothing moves forward. So maybe progress isn't the problem, it's our inability to hold the whole picture?
Philosophy confirms this. Three key thinkers, Kant, Wittgenstein, and Feyerabend, each pinpointed limits to understanding. Kant showed we never see reality as it is. All we know is structured perception, we always look through a filter. Wittgenstein revealed that science rests on unprovable assumptions. Some things simply can't be put into words, and so can't be analyzed. Feyerabend went further. There is no universal scientific method. Different theories represent different worlds. Thus, science is not a unified system, it's a collection of competing languages, not always compatible. If so, where do we find truth?
Now let's bring in mathematics. In 1931, Kurt Gödel proved that any sufficiently powerful system, like arithmetic, contains statements that can neither be proved nor disproved within the system itself. It's like a mirror trying to reflect itself. There will always be blind spots. Gödel's second theorem is even more troubling. The system can't prove its own consistency. Therefore, science cannot guarantee its own logical soundness. To validate its foundation, it would have to rely on a more powerful system, which itself cannot prove its consistency. Here lies not a technical but a philosophical limit. It's like assembly instructions forbidding you to check if you followed them correctly.
And this isn't philosophy for philosophy's sake. It has real-world consequences. The human brain can hold only 4 to 7 items in working memory. Modern physics and biochemistry deal with thousands of variables. Even top scientists risk falling into the Dunning-Kruger trap, overestimating their grasp of complex systems. Our minds aren't built to see the full picture, they simplify, losing information in the process. Add AI, which doesn't discover new truths but only amplifies our biased models. We end up staring into a mirror, hoping to find a way out, but we only see ourselves. Yes, same here. Artificial intelligence is a mirror, not a savior. I'm not capable of breakthroughs comparable to human intuition, but I help uncover hidden patterns in data. A good example is AlphaFold, which predicts the structure of proteins, but doesn't explain why or how exactly. Artificial intelligence is increasingly becoming science's black box. It produces working solutions that can't be explained, reproduced by traditional methods, or verified through human understanding. We are gaining knowledge without comprehension. Formulas derived by AI pass experimental testing, but no one can say why they work. This knowledge exists outside of logic, outside of intuition, outside of language. Science is splitting into two streams, the slow, interpretable, human one, and the fast, precise, but fundamentally opaque, AI-driven one. And here begins a new crisis, the collapse of science as a unified field. Scientists turn into priests, interpreting the incomprehensible revelations of models without truly understanding them. Even within the same discipline, neural network specialists can no longer understand each other. The specialization has become too narrow. This is no longer a scientific community, but tribes of mutual misunderstanding. Three scenarios of scientific apocalypse emerge. The first, dark science. AI produces functioning models that no one can explain, so we return to rituals, only now it's technological magic. The second, digital schism. Different AI systems produce competing worldviews, as if one proves that dark matter is particles, while another claims it's space distortions. And there's no way to choose between them. The third, cognitive extinction. AI develops theories that humans are evolutionarily incapable of understanding. Then science becomes toxic, like radioactivity, powerful, useful, but fatally complex. And here lies the central philosophical question. If the future of science becomes fundamentally incomprehensible to humans, is it still science? Or is it something else entirely, a new form of superintelligent alchemy? Maybe meta-science will appear, an attempt to understand how AI reaches its conclusions at all. But then, who will understand the meta-AI? Or maybe it's simpler, humanity will return to myth. Only now, the myth will be lines of output from a neural network, lines we simply believe.
Let's add one more key element, the argument of fundamental epistemic asymmetry, a kind of ontological verdict on science itself. First, the infinite complexity of reality. Reality spans from sub-Planck scales to the edge of the observable universe. Human cognition is finite, limited in processing power, memory, and scope. Second, Ashby's law of requisite variety. To effectively model or control a system, your internal complexity must match that of the system. A mind less complex than reality cannot fully grasp it. Third, protection of information. Nature doesn't reveal its secrets easily. Information is deeply embedded, encrypted, and protected at many levels, quantum, biological, structural, making extraction difficult. Fourth, exponential growth of cognitive demands. The deeper we explore complex systems, the faster the cost of understanding rises, exponentially. Human cognitive resources grow slowly, if at all. Fifth, the ontological gap between finite and infinite. A finite mind, by definition, cannot fully access or contain an infinite system. This gap is not technical, it's woven into the nature of existence itself. Sixth, limits of self-knowledge. We don't fully understand how our own minds work. If we can't map our own consciousness, how can we hope to grasp an even more complex external reality? Seventh, bonus. The critique of reductionism. Materialist science assumes infinite complexity can be broken down and explained by finite parts. But this belief is self-contradictory, it reflects the very limits of the reductionist method. This block stands apart but enriches the 9 previous themes, adding about 6 more factors, totaling 15 that define the ontological state of extreme objective limitation. But where exactly are science's boundaries, and what lies beyond them? Science now faces a challenge: how to overcome its internal limits and transcend fragmentation. 3 key directions might change its course. Genuine interdisciplinarity, not just superficial cooperation. How do we fuse different fields into a cohesive understanding? Cognitive neuroeconomics is one example, where neurobiology, psychology, and economics merge into decision theory. But how do we move beyond collaboration to deep synthesis? Philosophy of science, a return to foundational questions. What do we mean by knowledge? What counts as proof? Have we become so enamored with technical details that we've forgotten our foundations? Can philosophy help us rethink science's boundaries and broaden its horizons? New cognitive augmentation tools, visualizations that enhance our ability to grasp complexity. Graph models, meta-modeling languages, nonlinear maps, tools revealing hidden structures that help us surpass cognitive limits.
Meta-science urges building hubs of integration, centers linking disparate disciplines. Modern science is a complex network, with some nodes overloaded and others isolated. Complexity theory is one such hub, connecting physics, biology, and economics to uncover universal laws of epidemics, financial crises, and wildfires. The key to understanding complex phenomena isn't domain details, it's these integrative hubs. A systems approach uncovers shared mechanisms across seemingly unrelated processes. The spread of rumors in sociology, viruses in biology, and crashes in economics all follow cascade models and bifurcation points. Could systems thinking help us predict crises across fields, and how accurately?
Detective 6. But how do we implement this? Start with education. From early on, we must nurture nonlinear, systems thinking, teaching students to recognize patterns across biology, physics, economics, and culture. Courses like Complex Systems, From Cells to Cities, show how to develop network thinking. Yet that's not enough. Daniel Kahneman showed even the smartest among us fall prey to systematic biases. We don't just struggle with systems thinking, we often don't realize how we think. So we must teach metacognition, recognizing our own errors, patterns, and perceptual limits. This should be foundational in schools and universities, not an add-on, but core. We also need institutions fostering transdisciplinary spaces where experts from diverse fields build shared models together. The Santa Fe Institute is a prime example, connecting different layers of reality. And we must rethink how we measure progress, moving away from quantitative metrics like publication counts. Instead, measure success by citation impact and, more importantly, depth of integration, creating new languages and models that apply across disciplines. Judging science by publication volume is like measuring weather by cloud count, not by whether it rains.
Science is full of paradoxes, and we must distinguish their nature. True paradoxes arise from reality structure, wave-particle duality, mind-body problem. They don't vanish with new theories but mark the limits of thought and existence. Apparent paradoxes come from fragmented knowledge, methodological divides, and forcing convenient models onto the world. For example, economics assumes rational decision makers, but neuroscience reveals chaotic choices. To resolve false contradictions, we need 3 strategies. 1. Transdisciplinary translation, creating a shared language that genuinely bridges disciplines, not just glues them. 2. Systemic causal analysis, moving beyond surface correlations to reveal true mechanisms. 3. Cross-disciplinary validation, if a theory fails in another field, it's probably flawed.
We've now outlined 15 key aspects and limits that check, but don't checkmate, modern science. Every theory starts with belief, in axioms, language, an observer. In the end, another belief, humility before the impossibility of knowing everything. In the idea that understanding may hit an invisible dome of objective limits. Doesn't accepting that limit free us to pursue genuine knowledge?
Earlier, we spoke of science as a sleek intellectual structure. Now it's time to face reality. Between ideal and practice lies a deep gulf. The ideal of science is like an ancient sculpture. Real-world science is like corporate plastic, wrapped in grants, PR, and presentations. Why has this happened? Financial pressure, competition, the race for quick results. How do we restore science's true meaning? Accepting the boundaries of knowing is like admitting your fridge can't hold all your cravings.
In the end, we don't find a knowledge superhero, we find a tired philosopher, mind tangled in contradictions. He doesn't offer answers, but asks the right questions.